For thousands of years, the Atlantic Ocean has quietly run one of the most powerful machines on Earth, and most people never think about it. In February 2021, a winter storm dropped Texas into a deep freeze that killed over 200 people and knocked out power for millions. Some scientists pointed to a surprising possible contributor: shifting ocean currents thousands of miles away in the North Atlantic. That connection sounds strange. An ocean current off Greenland affecting Texas? But it's exactly the kind of link scientists are racing to understand right now, because the North Atlantic is behaving differently than it has in generations. In 2023, sea surface temperatures across the North Atlantic spiked to levels researchers called, in their own published data, statistically unprecedented. Numbers so far outside historical range that some oceanographers described being caught off guard by how fast they climbed. So here's the question driving this investigation. Is the Atlantic Ocean changing faster than we predicted? And what happens to the rest of us if it is? To understand why this matters, you first have to understand what the ocean actually is. Not a boundary between continents, not a backdrop. A machine, one of the largest energy transport systems on the planet, moving heat, salt, and nutrients across thousands of miles every single day, whether anyone is watching or not. And among all the world's oceans, the Atlantic runs one of the most important jobs of all. At the center of it is a current system scientists call the AMOC, the Atlantic Meridional Overturning Circulation. Picture the ocean as a giant conveyor belt. Warm water travels north on the surface from the tropics, carrying heat like an invisible river. Near Greenland, Iceland, and the subarctic seas, that water finally gives up its heat to the atmosphere. And that heat is one of the reasons Western Europe stays milder than other regions at the same latitude. But the process doesn't stop at the surface. As the water cools, it gets denser. Add in high salt content and it gets denser still. Eventually it does something dramatic. It sinks. Thousands of meters down, all at once, in specific regions of the North Atlantic. That sinking pulls more warm water in behind it from the south, and the loop continues. A cycle that has run, largely unbroken, for thousands of years. Scientists have only been able to measure this system directly since 2004 through an observation network called RAPID, anchored along 26.5 degrees north latitude, tracking temperature, current speed, and water transport around the clock. What that network has picked up is not simple. The AMOC naturally wobbles year to year. A strong year here, a weak year there, shaped by short-term weather patterns like El Niño. Separating that noise from a real long-term trend is like watching traffic on a highway. One car speeding up tells you nothing, but watch the flow for long enough, and a pattern emerges. Zoom out across decades, and a pattern has emerged. Climate models increasingly agree that continued global warming is very likely to weaken this system over the coming century. Here's the mechanism. The AMOC depends entirely on cold, salty water being dense enough to sink. Two things interfere with that: heat and fresh water. And both are happening at once, right now. Greenland is losing ice at a pace unlike anything in the recent geological record. Recent satellite estimates put the loss at roughly 270 billion tons of ice per year. Every ton of that meltwater pours straight into the North Atlantic as fresh water. Fresh water is less dense than salt water. Less dense water resists sinking, and water that won't sink can't power a conveyor belt built entirely around sinking. At the same time, the ocean has absorbed more than 90% of the excess heat trapped by rising greenhouse gases since the industrial era began. The ocean has essentially been shielding us from a far hotter atmosphere, quietly taking the hit so we didn't have to. But that shield comes at a cost we're only beginning to measure. Now, before this starts sounding like the plot of a disaster movie, no credible scientist is claiming the AMOC is about to collapse overnight, and nobody serious is predicting Europe is about to freeze. That version of the story is a media exaggeration that keeps resurfacing every few years. What the actual data shows is a gradual weakening, and in a system this large, gradual can still mean consequences serious enough to reshape entire coastlines and economies. You don't have to look far to see it starting. Take Miami Beach. Sunny day flooding, salt water bubbling up through storm drains with zero rain in the forecast. Used to be rare enough to make local news. City records now show it happening dozens of times a year, driven by a regional sea level rise that's now outpacing the global average across parts of the U.S. Southeast. Roads and drainage systems engineered in the 1980s simply weren't built for the ocean sitting outside them today. Or look further north, to the Gulf of Maine, one of the fastest warming bodies of water on the entire planet, warming faster than roughly 99% of the global ocean, according to research from the Gulf of Maine Research Institute. Cod stocks that sustained fishing families for generations have collapsed. Lobster, the region's signature catch and its economic backbone, is migrating north into Canadian waters as local temperatures climb past what the species can tolerate. Entire multi-generational fishing operations are being forced to adapt to a map that no longer matches the one their grandparents fished. These aren't hypothetical futures scientists are warning us about. They're happening right now, on the same ocean, in the same decade that satellites are watching heat pile up in the North Atlantic. And there's a deeper reason researchers are watching so closely. The AMOC isn't a system that only ever changes slowly. Buried in the seafloor are sediment cores, layers of material that have built up for tens of thousands of years, each one a page in a very long book. When scientists drill into them and analyze what's preserved inside, they can reconstruct ocean temperatures and circulation patterns from the deep past. And what those cores reveal is unsettling. During the last ice age, this circulation system underwent rapid, dramatic shifts, sometimes unfolding over the course of just decades, not centuries. Regional temperatures swung by several degrees within a single human lifetime. That's the part that keeps climate scientists up at night. Complex systems like this don't always change in a straight line. Push them hard enough, and they can flip into a different state far faster than a gradual model would suggest. Researchers call this a tipping point. Imagine a ball resting on a gently sloped surface. Small nudges don't move it much, but push past a certain threshold and it doesn't slide, it drops. The honest answer right now is that nobody knows exactly how close that threshold is. Estimates for significant AMOC weakening span the rest of this century, and the precise timeline remains one of the most actively debated questions in climate science today. That uncertainty isn't a failure of the science. It's exactly why monitoring networks like RAPID exist, and why ocean observation budgets have expanded dramatically over the past 20 years. Because the cost of being surprised by this system is far higher than the cost of watching it closely. So, what would a weaker AMOC actually mean beyond the ocean itself? Heat would get redistributed differently across the planet. Some models suggest parts of the North Atlantic region could see relative cooling even as the rest of the world keeps warming overall. A genuinely counterintuitive outcome that researchers have to work hard to explain because it sounds like the opposite of global warming while actually being a symptom of it. Rainfall patterns that farmers and cities have planned entire seasons around for generations could shift. Fisheries would keep reorganizing, the way they already are in Maine. Coastal infrastructure engineered for one ocean would keep facing a different one, year after year, storm after storm. None of this stays contained in the water. That's the real story here. A block of ice melting off Greenland today can, through a chain of physical cause and effect, contribute to a power grid failure in Texas years later. A current shifting off the coast of West Africa can end up as an empty net on a fishing boat off the coast of Maine. The ocean doesn't recognize the borders on our maps, and it never has. We used to think of oceans as too vast to change, too big for anything humans do to actually move the needle. The data says otherwise. The Atlantic is telling us, in record temperature readings, in fish populations relocating hundreds of miles, in streets flooding under a clear blue sky, that the system our cities, our food supply, and our climate were built around is already shifting beneath us. The question was never really whether the ocean would change. It always has, across the entire history of this planet. The real question, the one scientists are racing to answer with every buoy, every satellite pass, every sediment core pulled from the seafloor, is whether we're paying attention fast enough to adapt to the ocean we're about to get next. If you want to understand what's happening to the ocean before it shows up on the evening news, subscribe. Because the Atlantic isn't the only current shifting right now. The Pacific is running its own quiet experiment, and it's just as strange. That's next.